Hello everyone, today I want to explain my homework 5, homework 3, exercise 4.1. Write a C hash to control C++ language by control stepping model. Let's start it together. First, this position is divided into 6 parts. First, I will introduce the overall goals of the project. Next, I will detail the record, hardware, and circuit connection. Then, I will analyze the C++ code on the Arduino side and the C hash code on the PC side separately. After that, I will demonstrate the entire system workflow through the flow chart. Finally, I will simulate the key knowledge points involved in the project. First, let's introduce the background and the objective of this project. This project is our cross assignment with the core task of achieving cross-language control. That is using a desktop program writer in C hash to control C++ code on the Arduino. Alternatively, driving a stamper model. Through this project, I aim to achieve 3 main goals. First, to deeply understand the mechanism of several communication. Second, to master the divide principle of stamper models. And third, to personally build a complete control system. To complete this project, we need to prepare some hardware. The core components include Arduino Uno board, which acts as our microcontroller responsible for directly controlling the model. Then there is the 28 BYJ and 48 stamper model and ULN 2003 driving model, which is used to amplify the output signal from the Arduino to drive the model. Additionally, we need some chapter wires to connect the peripheral components, USB cable for communication, and power supply between the Arduino and the computer, and of course a computer with the No.3 development software installed. This is our circuit connection diagram. As you see, digital pin 3 to 6 of the Arduino are connected to the 4 input pins of the ULN 2003 driver model. Respectively, the output terminal of the driver model are then connected to the coils of the stepper model. In this way, the Arduino can command the driver model by controlling the high and low levels of these 4 pins, thereby driving the model to rotate. The diagram clearly labels the connection relationship between each part. Next, Let's look at the C++ code on the Arduino side. This is the overall structure of the code, which is mainly divided into 4 parts. First, the definition of pins and the driving instructions, which is the basis for controlling the model. Then the setup internalization function, responsible for preparation the crew logical is in the loop main loop, which constantly listens for several commands and controls the model. Finally, there is a helper function set model pins to set the model pin levels. We will press each part next. First, look at the beginning of the code. 4 pins are defined here, corresponding to pins 3 to 6 of the Arduino, which is consistent with our planning during hardware connection. More importantly, this step sequence error is an 8-row by 4-column error storing combination of 0 second and 1 second. This is actually the dance steps to control the rotate of the 28 BYG 48 model, which we call the 4-pass 8-bit driving sequence. Each row represents a state, and execute these 8 states in sequence will rotate the model by a fixed angle. Next is the setup initialization function. Here the pin mode function is first used to set all 4 pins controlling the model to output model. Then a very critical step is to internalize several communication with several pins, setting the bound rate to 9600. This parameter must be actually to same as the setting in the C# program later. Otherwise, the two will not be able to communicate. Finally, the set model pins function is called to set all 4 pins to low level, so that the model is in a stopped state from the beginning, which is a safe internalization operation. Now let's look at the crew loop main loop, which runs continuously. First, the program checks if there is any data coming through the several ports. If there is, it reads a chapter, which is the command set by the C# program. Then through a switch statement, it determines whether the command is 0, 1, or 2, corresponding to stop, forward, and reverse responsibility, and sets the corresponding model step. Finally, according to the model step, the program calculates which bit in the driving sequence should be executed next. Then sets the model pins to rotate the model. The delay 10 here is used to control the speed with a delay of 10 milliseconds, which can be adjusted as needed. After looking at the code on the Arduino side, let's look at the C# program on the PC side. This is the running interface of the program, which is very simple, with a several port selection box, a connect between and 3 buttons to control the forward, receive, reverse, and stop of the model. The main job of the C# code is to handle these UI interactions and communicate with the Arduino via the several ports. The code structure is mainly divided into 3 parts: several port management, UI event heading, and date transmitting reception. First, let's see how the C# code handles the several ports. When the program starts, it automatically finds all available several ports on the computer and displays them in a drop-down box, so the user doesn't have to enter them manually. When the user selects the correct several port and clicks the connect button, the program configures reverse permits of the several port, such as the port name and baud rate of 9600. These permits must exactly match those on the Arduino side. After configuration, the open method is called the open the several port, so that the C# program and the Arduino installation communication. Next is the UI interaction part. When the user clicks the forward, reverse or stop buttons on the interface, the program triggers on the corresponds click events. In this event handling functions, instead of directly operating the several port, a method called setSeveral command is called, passing in the starting 1, 2, and 0. Responsibility this setSeveral command method is a encapsulate function and checks if the several port is already connected, and if so, sets the command to the Arduino. This design makes the code clear and easier to maintain. Now let's starting together to the workflow of the entire system. First, we need to complete the hardware connection and upload the Arduino code. Then run the C# program. Select the several port on the interface and click connect. After that, when we click the forward button, the C# program will set the command 1. After receiving this command, the Arduino will pass it as a forward command and then drive the model to start retooling forward. The entire process is such a complete closed loop from user operation to hardware execution. Let's look at the video. This is the final diamond effect we have achieved. The user only needs to select the correct stable port on this simple interface, click connect, and then control the modules forward, reverse, and stop with 3 buttons. The entire operation is very intuitive and convenient, achieving the expected goals of our project. In summary, this course assignment successfully achieved the goal of countering a stamper model driven by C++ using C#. Through this project, I not only reviewed and considered relevant hardware and programming knowledge, but more importantly, exercised my complete engineering practice ability from requirement analysis to final implementation. This simple control system also lays a good foundation for more complex projects in the future. That's all for my homework. Thanks for your listening. See you.